All right, so we got about 1.5 minutes before I start the actual lecture. And good morning to everybody. I know it's a little bit late in the morning, but it's still morning. So all right, so what we're going to do today is we are going to talk about functions. And when we talk about functions, it's going to be from the context of this class. So it may look a little bit different compared to your other classes, especially calculus, because calculus deals with mostly continuous math. And in this class, we deal with mostly discrete math. So it's going to be a little bit different. On my webcam. Okay. Oh, I forgot to turn on the lights too. So let me turn on the lights. Okay, so what about the OBS?
You're good now.
Oh, okay. Yeah, I have to play with the color settings of the camera a little bit. This one doesn't have a very good white balancing feature built into it, so maybe I'll just kind of turn it into black and white because it looks like I'm the Hulk without the Hulk. Just look green and gamma radiated. All right. All right, so it's 20 seconds past 10:30. I'm getting started here. All right, so we are pretty much done with set theory, including set theory using quantifiers. I can go into the quiz if there are any questions about it, or if nobody cares and if everybody thinks well, we pretty much got the quiz, then we don't have to go into the quiz. So does anyone want me to go into the quiz? Okay, great. We can do that. All right, so here's the quiz, and I'm putting this into preview mode, so it's very similar to what you would see when you took the test. All right, so here's question number one. Question number one asks which of the following is true. So the first one is A is a subset of B. So in order for A to be a subset of B, every element in A should be found in B. So we look at each element. A is found in B. We look at element B, which is also found in the set B. So I would say the first one is probably the correct answer, but we're going to check the rest too, okay? Because we want to make sure and confirm all of the other options are not true. The set A, uppercase A, is an element of the uppercase B, which is a set, and that is false. Okay, because the set A, which has elements A and B, is not itself an element of uppercase B as a set. Okay, and the third choice is B is a subset of A. That is not true because B has an element C that is missing from the set A, so that is not true. And the last one is B is an element of A. That is also not true because the set A, every element of the set A is a symbol value. It is not a set itself. So there's no way the set B is an element of A as a set. So that's why in question number one, A is a subset of B is the correct answer. So if I don't see any questions in the text channel, I'm just going to move on. In question number two, it says, given that A union B is A, B, C, D, E, or contains lowercase a, b, c, d, e as elements, and A minus B, set A minus set B, has the two elements C and E, define a membership arrangement. In other words, we want to be able to specify what elements are in A and what elements are in B in order to satisfy these constraints. Enter your answer. Yeah, go ahead.
Would it be that A is A, B, C, D, E, and then B is A, B?
There are several answers. Okay, so it doesn't have a unique answer. It has several answers. As long as your answer meet the constraints, which is specified here. So the union of the two sets, it has to contain A, B, C, D, E. And then elements that are in A but not in B, they have to be C and E. So as long as that constraint is satisfied, you can define the sets any way you want. Okay. So let me give you one kind of extreme case. Okay. So we can define A to have all A, B, C, D, E. Okay. Lowercase a, b, c, d, e. So now I just have to make sure that B does not contain C or E, because A minus B, contains all the elements that are found in A but not in B. So I just have to make sure that I have to be careful with B, so that B does not have C and E. So I can say B still has A, B, and D. As long as C and E are missing from B, I have met the constraints. Does that make sense?
In this case, the result is only what is subtracted from A, not what's subtracted or what's left from both A and B.
Are you referring to the notation A minus B?
Yes, because I thought that, so if we take A minus B, whatever is in A and B gets subtracted out, and whatever is left gets, or is what's the resulting subset.
It is whatever. Okay, so if you look up the definition of a set, the subtraction of two sets, it basically just says, if you're looking at A minus B, you're looking at all elements that are in A but not in B. That really is the definition of the minus operator between two sets.
Okay.
So the homework assignment, which is in the form of a quiz, but since there's no actual time requirement, is really just trying to make sure that you guys know where to look up the definition and understand what the definition is saying. All right, so are we good with number 2? Sorry about scrolling along a little too fast. So are we good with this one? Number 2? Okay, excellent. So now we move on to question number 3, which is asking, is the value A, or the value, is the value A in the set that has a set of A in it? And the answer is false. Okay, this is actually false, because this is a single element, and the only element in the set that we're concerned about is by itself a set. So they do not match. The element or the value A cannot match the set that has the same value. They do not match. They are not considered equal. All right, so are we good with number 3? Okay, looks that way. So when will
we be able to see our quiz?
I think now now that it is past due, if you refresh it, you probably will see your answer. If not, I can go back and check the settings. Oh, there's only one that needs to be manually graded, which is number 2, if I remember correctly. That's the only one that needs to be manually graded. So the other ones, I think Canvas will tell you whether you got the other ones right or not.
It looks like they all need to be graded.
They all need to be graded. Okay. But since I'm talking about the solutions right now, so you can actually take this one and use this part of the lecture to understand whether you got it right or not. All right, so I got a question from the text channel. Alex is asking, since a set needs all unique values, would the set A and would the set that contains A and a set that contains A still be a set? The answer is yes, because A and the set that contains A are considered two different things. We talked about equivalency of items, and if one is a set and the other one is not a set, they cannot be the same thing. Yep. Okay. So question number 4 then. So question number 4 is asking whether the set ABC is a subset of the set ABC. The answer is true. A set is a subset of itself, always. Now, if this one doesn't have a bar under it, in other words, if I'm asking whether ABC is a proper subset of the set ABC, then the answer would be false, because in order to be a proper subset, if A is a proper subset of B, then B has to contain elements that cannot be found in A. But I'm not asking whether it's a proper subset, it is just subset of, so that's why the answer is true in this case. Question number 5. So question number 5 is asking if I have a union, and the first set in the union is ABC, or ABC in the set notation, and then the second set is just AB, in braces, then is the answer ABC, then the answer is true. Okay, this is actually true. And then we move on to question number 6. Question number 6 is a little bit more tricky because it's asking you, regardless of the definitions of set A and B, is this implication true? Okay, in other words, if you can find one case, okay, to define A and B, and it will make this implication false, then the answer is false, okay, because this implication is not always true. All right, so let's check this out. The left-hand side, so the key to find the answer to this one is to see if you can find a case where the left-hand side of the implication is true, but the right-hand side of the implication is false. Okay, so we'll work on this one, and I'm gonna show. I know it's hard for you guys to see it, but this is the only way I can type the example, while I'm still looking at it. Okay, so we want A minus B. Okay, let me use the math equation here. So we want A minus B to be the empty set, and we want that to be true. We want that to be true, and we want the other side to be false. So if we want the negation of A is a proper subset of B to be false, we are really just asking, can we make A a subset of B? Okay, so if I go back to the preview, that should be correct. There we go. So we want both of these to be true. Okay, so if you can find a case where you can make this happen, then it's the answer is going to be false. So let's see if we can make the first one, both of these to be true. So we are looking for a proper subset A of B, and if A is a proper subset of B, then A minus B is guaranteed to be an empty set. So that means this cannot happen, or at least as far as I can see right now, this should not be able to happen, because if A is a subset of B, then if A minus B is an empty set, then we cannot. Oh, okay. So if A minus B is an empty set, A and B can contain entirely different elements. So that is false. So we want it to be true, and the second one we also want it to be true. Yeah, go ahead.
So just looking through this, so A will always be a subset of B, and so the answer for this one you said was false, correct?
Well, if we can find a case to make what you see on the screen happen, A minus B is an empty set, and A is also a subset of B, then the answer is false.
Well,
And
is A always going to be a subset of B?
proper subset of? So not always, but we can make it happen, right? So the answer, okay, so I know how to answer this now. So we can make, okay, so these are the constraints. Okay, what I'm listing here are the constraints. So now I'm going to give you what can meet these constraints, make these constraints both be met. Okay, so we can make the set that contains the element X. You cannot see what I'm typing right now because I have to finish that first. So we can make A like this, and then we'll make B a superset of A, which means it will contain X and one more element, at least one more. So B is just XY like this. So let's see if this makes both constraints. Let's see if this is meeting both constraints. So we go back to the first one, which is A minus B is in an empty set. Is everything okay, let me put it the other way. Okay, so is the set containing everything in A but not in B an empty set? Yes. Okay. And then the second requirement is A a subset of B, a proper subset of B? Yes. So since both of these are true, then we go back to the question. So we are now making A minus B equals to empty set true, but at the same time we are also making it A is not a proper subset of B false. So now we have true implies false, which means the entire thing is false. So now, because I can find one case, okay, because I can find at least one case as an example, you know, of the values of A and B to meet those constraints. So now I have to answer false because the question is asking regardless of the definitions of set A and B, the following is true. Well, since we have just found a counter example to make that expression false, then you know that what the question is asking is false. Is that okay? Okay, all right. So moving on to question number 7, you know, more stuff kind of like this. So it's the same thing. So we want to ask the question, can we make the left-hand side true, but the right-hand side false? Okay, that is the question. So the left-hand side is saying the intersection of the two sets is the same as the union of the two sets. Okay, and then the right-hand side is saying A and B are really the same thing. So can we make the left-hand side true, but the right-hand side false? If we cannot, then we have to answer true. But if we can find at least one case that satisfies that particular constraint, then we'll answer false. So what do you guys think? You have to kind of go back to the definitions of intersection versus union. So the intersection means, you know, everything that is in the intersection can be found in both A and B. The union says everything that can be found in the union can be found in at least one of these two, you know, A or B. So if the intersection equals to the union, it does imply that A and B are the same. In other words, you should not be able to find a case where the left-hand side of the implication is true, but the right-hand side of the implication is false. That should not be possible, and we should answer true in this case. So for the people who think the answer to this question should be false, then you have to present me a counterexample, because you know, that is what you need in order to justify the answer of false. Are we doing okay so far with this?
Yeah.
Okay, cool. Thank you. Moving on to question number 8, which is the last one. And this one is also a little bit tricky, so we'll do it exactly the same way. You know, we'll basically say, can we find a case where the set A is an element of the set B? However, it is not the case, okay, it is not the case that A is a subset of B is false, okay? So we have the negation being false, which means we're really just looking for A being a subset of B. So we are asking really, what we are really asking is, can we find A being both an element of B and also a subset of B? So that should be possible. So let me go to this part here, and actually I take it back. I'm going to go back to the question first because I need to copy the constraints, and then we'll work on the example. So the first constraint is A is an element of B, and then the second constraint is A is a subset of B. Okay, so now we can go back to here, and we are now focusing on these two. Okay, So A is a subset of B is pretty easy to make happen, but we also want to make sure that A is a subset of B. So I think I presented an example just like that in the previous class. I think I did it in the text channel too. I'm not 100% sure, but I think I did. So what we need to do is to make sure that A is defined to be a set, and it can have anything. Okay, we'll just have a single element of X in A.
Could you put some sort of divider between the first question and the second question?
Yeah, we can do that. Do you guys remember which question this was? Okay, I'll just look it up. This is question number 8, and the other one was question number 6. Okay, so we can do it like this. This is for Q6, and this one is for Q8. And then do the proper indentation, right? So there are 4 lines here, and then there are 3 lines at this point. And it's not, oh, there we go. It just took a little bit of time. Is that good?
Perfect.
All right, excellent. So now we have to construct B. So the way we construct B is so that B has to satisfy both constraints. B has to be a set containing the set A. Okay, so B itself is a set, and it has to contain the set A as an element. So this is what we have at this point. Okay, this will require the first constraint, but it doesn't satisfy the second constraint. Does everybody see how the way I define B right now only satisfies the first constraint of A is an element of B? Because A is a set that has X in it, and B is a set that has the set of X in it. So that's why A, the entire set A, is an element of B, the way it is defined at this point. So is that okay? So we have met the first constraint, but we haven't met the second constraint, because at this point A is not a subset of B. A and B have different elements, so they're just considered different, but one is not a subset of the other one. So to meet the second constraint, all we need is to have X to be inside the set of B, then it satisfies both requirements. So the way B is defined right now, the first element that we list in B meets the first constraint. And then the second element that we list in B is satisfying the second constraint. And now we have A and B satisfying both constraints, which means the answer to the question is going to be false, because we have just made a case so that the left-hand side is true, but the right-hand side is false. So are we good so far with this? Okay, I'm not seeing any questions, nor confirmation that we are okay. So
Could you say it one more time?
we have made a condition. Okay, let me see if I can peel this off so we can see both at the same time. Okay, yep, okay, that will help. But I have to make sure that they're both within the area that you guys can see. There we go. All right, so are we agreeing that A is an element of B is true? A being defined as the set that has X in it, and B is defined to be a set with 2 elements. The first element is a set of X in it. Okay, so that meets the first constraint. So the second constraint is we have to make the right-hand side of the implication false. So we are looking at the negation of something being false, which means whatever is being negated has to be true. In other words, we are looking for a case where A is a subset of B. So when we look at this example here, A is a subset of B is actually true, because everything in A can be found in B. A only has a single value of X, and B has that particular value, even though it has something else, but it has the element that we have in A. All the elements in A can be found in B. So that means, we have just constructed a case where the left-hand side of the implication is true, but the right-hand side of the implication is false. So if I can find at least one example of set A and B to make this entire thing false, then the statement of regardless of the condition of the definitions of set A and B, blah, 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 that whole statement is now false. So that's why we have the answer false here.
Okay.
Yeah, to use quantifiers, okay, I know, this, it doesn't use quantifiers, but to use quantifiers in this context, this question is really saying, okay, let me write it here. That will make it super clear, okay? So the question is really asking, you guys cannot see it yet, because I have to finish this first. So for all A being a set, for all B being a set, and then we have what we have in the implication here, A in B, right arrow, negation of A subset equal to B, close that, close that, close that, close. Oh, there we go. There we go. All right, so let me drag this over a little bit because I think some of the text is outside of the area that you guys can see. So the question is really asking this, okay? Is this expression true? For all set A and for all set B, A in B implies it is not the case that A is a subset of B. But since we just found that there's one case, there exists, right? There exists A and there exists B, such that this expression is false. When I say that expression, I mean this one here. So we can make this false for at least one instance of A and B. So that means this entire thing is false. And that's basically what the question is asking, without using the for all quantifier. So are we okay so far with the assignment? Okay.
Yep.
Okay, very good. And if I submit the quiz, I should get points for everything except for the manually graded question. So let me just double check. 1 of 1. This is the only one that the computer cannot assign the grade automatically. So for everything else, I should get 1 out of 1 point. Yep, so that's all good. So I need to grade this manually because just one of the questions need to be graded manually. So you won't see your actual grade until I do that. But I think for the most part, you guys already know what grade you're gonna get, right? Because we kind of know the variations of question 2. So in question number 2, the variations, I mean, it really boils down to the way you choose membership of A and B. When you compute the union of the two, do you get A, B, C, D, E back? And when you look at everything that is in A but not in B, do you get C and E back? If it meets that requirement, then you get full points for that particular question. All right, so that is the quiz that we have. And let's see, nope, this is not the right tab. All right, so now we are moving on to functions, okay? But we are looking at functions as sets. So that is a little bit tricky because this is not the way you look at functions in your calculus class, nor normal algebra classes. So we'll take a look at this particular module. And the first thing I want to talk about are tuples. Now we know tuples already because we talked about Cartesian products. So a tuple is basically, quote unquote, an array with a fixed width. So when we say, a 2 tuple, that means it is a tuple that has exactly 2 items. Unlike a set, a tuple can contain duplicate values, and the ordering of things is also important. And that's why the tuple, this is called a 3 tuple, because it has 3 elements in it. But we can just say it's a tuple in general. So the tuple 1, 1, 2 is considered different from the tuple 1, 2, 1 because we have to match not only whether a value in the first one is found in the second one, but it has to be found at exactly the same place. So position is important in a tuple. A tuple is represented by a comma-separated list of items enclosed in parentheses. Now, we have seen that already, okay? We have seen it when we talked about Cartesian products, but this is just another place, another reminder of how we look at tuples. And I would use T bracket I to look at a specific item inside a tuple. So if T is a tuple, then T bracket I is identifying the item I of the tuple. So the best way to look at this, instead of looking at it as ith item, the best way to look at it is item I, okay? Because otherwise, we get into the kind of really weird way of using words in English, because instead of using first, okay, which implies the use of one, we have to say the 0th item in a tuple. So if you say item 0, it's actually better. It makes more sense instead of 0th item. Let's see, and we'll also borrow the cardinality notation. So if T is a tuple, then bar T bar specifies the number of items in the tuple. It's basically the length of an array. So are we good so far with the notation of tuples? Because that's really kind of the first thing we need to do, is to clear up on the notations of a tuple. But for the most part, we're just looking at a tuple as an array. So it's not a super, it's actually not a difficult concept, considering that arrays are in just about any programming language. It's just that we have to remember, instead of using square brackets or curly braces to enclose items in the array, we have to use round parentheses, okay, because that's the mathematical notation that we use in this class. I'm not seeing any questions, so I am going to continue with the lecture. So now we actually get to define we start to look at what a function is, okay? So in your math class, you're probably familiar with the way of defining a function f, as f of x is 2x. In other words, function f is really more or less a shorthand, because the actual definition of the function can be a lot more hairy compared to just 2 times x, okay? So f of x is kind of really just it's more like a subroutine, okay? When you look at it, it's more like a subroutine, so that you have a complex function, but instead of having to repeat the entire complex function, you just say, okay, it has got one variable that in this case that we care about, and it is defined to be like this. But 2x can be a very complex expression itself, and we don't really care, okay? Because we are just trying to look at a function as a shorthand. But in this class, the way we look at function is, it is just a mapping, okay? It's a mapping that maps elements from one domain, okay? So the domain is a set, okay? When I just use the word domain, it is implying that it is a set. So a function maps elements in a domain to another set, which is called a codomain. Now, the domain and the codomain can be the same set, or they can be different sets, okay? So there's no limitation of what you can use for the domain and what you can use for the codomain, okay? They can be the same, they can be entirely different, they can overlap a little bit, one can be the subset of the other one. All of those things can happen, okay? So there are no explicit constraints as to how the domain and the codomain need to relate to each other, okay? So here we move on to a little bit more notation. So this notation, f colon x points to y, Discord just crap out. Just let me go back to Discord. And let's see, are we back? Yep, I'm back, but I have to reshare the screen. Actually, it did. Okay, this is funny. It actually, quote unquote, did not crash. What it did was it found out that there's an update, and it went ahead to update itself without asking me or warning me that it was about to update itself. Alrighty, yeah, yep. But we're back. Okay, so that's the good part. Nope, this is not using Windows. This is probably just Discord. There's probably a setting somewhere, that says, if there's an update, it does not apply the update by itself automatically. So I'm gonna have to find that setting, after the class. Omar is acting like Windows. Well, but it's just one application, so I would blame it on the app itself instead of the operating system. Well, that's why Discord is hiring, right? They have a lot of open positions. Oh, okay, I see. Yep. Guess what all those new software engineers that Discord is hiring going to do? They're not going to implement new features. They're not going to do anything quote unquote cool. They are going to debug Discord. That's what most new engineers do, software engineers do when they first get hired, is to fix things. There we go. All right, so can I assume everybody is back? We can all see the screen share again. All right. Okay. Well, I'm not seeing any text saying that they cannot see the screen, so I'm just gonna assume everybody is back. All right, cool. All right, so we're gonna get back to this notation, F:(x), and then a single arrow, not a double bar, it's a single bar arrow to y. So what this notation is saying is f is a function, x is the domain, and y is the codomain. In other words, the other way to say this is f is a function that maps x to y. Okay, that's kind of the English words to describe the same thing. So now we want to look at f as a set. Okay, so once again, the big difference between what we are talking about now compared to Algebra 2 or most other math classes is we look at a function as a set. Okay, so now what we want to do is to use an example. Okay, so we'll use the example like before, which is f of x equals to 2x. This is how we define function f in a normal math class. Okay, so the first thing we need to do is to identify the domain. Okay, so what can we use as x in this particular function f of x? Now f of x equals to 2x, that works in, x can be a real number, it works. X can be a complex number, it works. And x can be an integer, it works. X can be a natural number, and it works. Okay, so we kind of have to limit what kind of value can x be. Okay, that is how we identify the domain. In this class, we are not concerned about real numbers, so we're going to use mostly integers and natural numbers and counting numbers. So in this case, we are going to limit the domain to be the set of all integers, which is the funny looking z. Okay, and then the codomain, let's assume for now that it is also the set of all integers. So in other words, the way we look at this particular function here, okay, we are now putting some extra constraints and say that the domain is the set of all integers and the codomain would be the set of all integers as well. So now how do we convey that, convey what is in the set? So when we look at this particular function, we can enumerate some of the elements in the set. So the first element here is saying this 0, the first 0, is coming from the domain. The second 0 is what that 0 is mapping to in the codomain. This 1 is once again coming from the domain, and the value of 1 is mapped to the value of 2 in the codomain. 2 is mapped to 4, 3 is mapped to 6, and so on. Okay, so once again, this notation, okay, the notation we're looking at here, which has the dot 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 or the ellipses, it conveys more or less what we want to do, but you can never be really sure that the next item really is 4, 8, and then the next one is 5, 10, and so on. Okay, As a result, we want something that is more precise, okay? We want something that is going to tell us exactly what is in this particular set F. But before we move on to that part, is this okay? Is everybody understanding how we are looking at a function as a set? Each element of that particular set is telling us how we map a particular value in the domain to the value that it needs to map to in the codomain. Is that okay? All right, cool. Okay, I got one confirmation that it's good. All right, so I'm gonna move on, okay? So what we want to do is to use a more concise and more accurate description. So I can do it this way too, okay? Now, if you remember, this bar notation here, it is basically saying, x to x, and x being an element of the set of all integers. That is the constraint, okay? This notation here, okay, what we see here is really saying the same thing as what this notation is saying. It's basically saying, for every x in Z and for every y in Z, y equals to 2x if and only if xy is an element of F. Now, this is important. This is if and only if, not just if, okay? Not just implication in one direction. It has to be if and only if, because we want to make sure that if you can find an integer x and then you can find an integer y such that y equals to 2x, then xy, you better be able to find that in the set F. On the other hand, if you find something in F, okay, which has the first item being x and the second item in the 2 tuple being y, then you better make sure that y equals to 2x. That is what we are saying here. And by the way, today's row-taking word is if and only if, spelled as just IFF in lowercase. So I'm gonna make it super clear, and let's see, do I still have that? Yep, I still have it on the side here. All right, so today's row-taking word is IFF. It's just if and only if. All right, so Alex is asking questions, so is Gary. It's showing multiple choice. Oh, I forgot to change the settings again. Great, okay, well, then you cannot. Okay, if anyone is getting this one wrong, I'll be very, very disappointed. I really should not be laughing because somebody actually might do that. Yeah, I don't get easily surprised anymore. So if somebody actually click on the bubble that has nothing next to it, I'll just say I'm not surprised. All right, so moving on. Okay, so I hope you guys got that done already. Get it out of the way. So, all right, so what we want to do is now to really take a close look of what makes a function a function. Okay, so this is really kind of important stuff because it has to do with the constraints of when we call a set a function, what are the constraints that we need to meet in order to be able to call a set a function. Okay, so there are a few things. So if I claim that f is a function that maps domain x to codomain y, the first thing that we need to make sure is f as a set is a subset of the Cartesian product between x and y. That's the first constraint. Okay, if f is not a subset of the domain Cartesian product with the codomain, don't even bother. Okay, f cannot be seen as a function. Is that okay? So that's the first constraint. Are we understanding that this is the first requirement of that? In order to say that f maps domain X to codomain Y, f first needs to be a subset of the Cartesian product between the domain and the codomain. It kind of makes sense, right? Because every single element of f is a two-tuple, where the first item is a value from the domain, and then the second value is a value from the codomain. Uh-oh, it craps out again. All right, so Discord just crapped out again. There wasn't any doing on my part. But I do notice both times, okay, before it crapped out, there was a ding, probably from one of my browsers. So maybe my browser is interfering. So I'm gonna close the tab on my browser that was kind of dinging me, right before it crashed. So hopefully it will get more stable this time. I don't know. I'm not paid to debug Discord. Cool. All right. So I'm hoping everybody is back. Is that true? Okay. Let me just ask on the text channel. Okay. Cool. All right. Excellent. All right. So getting back to what makes a function. This is the first requirement. The second requirement is a little bit harder to describe, okay? So if I were to say it in English, okay, it is going to be this statement down here, okay? I'm going to highlight it so that we can just kind of focus on this sentence here. So in order for f to be a function, okay, each element of the domain, which in this notation is our set X, must be mapped to one and only one element in the codomain, which in this case we call that our set Y. Okay, so let's do a few examples to see how this requirement can be met and also not be met at the same time. Okay, so we want to use a few examples to illustrate it. So let me put this back into the center. Okay, so this way we can see the entire thing. All right, so, and we'll make a new point here. Okay, examples of functions and not functions. There we go. There's a short delay now, it should update. It updates when I press the update key, but it doesn't seem to automatically update. Okay, maybe, I just need to fix a few things, but it's okay. It's not exactly one-to-one. We'll get to one-to-one when we talk about bijection. So what we need to do is to first use an example of what X can contain. So we'll say X has the elements A, B, and C. There we go. And we'll say Y, which is our intended codomain, would have the values 1, 2, and 3. Okay. So in this case, this is how I choose my domain and the codomain. Okay. X as our domain has only 3 elements. Those are the lowercase letters A, B, and C. And then Y as our codomain has the values of 1, 2, and 3. You guys cannot see why because I haven't. Okay, I think I know what I need to do to make it show. There we go. Okay, so I just need to press the escape key in Vim, because I actually changed the setting so that you guys won't see the equations before they're fully done. All right, so let me give you an example. Okay, so let's say f. You cannot see it just yet. Okay, so if f is just, okay, we'll make it an empty set. Okay, that makes it super obvious. So now is f a function that maps the domain X to the codomain Y? And if it is or is not, can you tell me why? So is it or is it not a function, the way f is defined at this point? Okay, so let me just put it extra clear here. Is f a function such that f is mapping x to y? Okay, well, the answer is, okay, does it meet the requirement that I just said in English? In other words, does it meet the requirement of every element in x needs to map to one and only one element in y? Is that happening with the way I define f in this case? No, exactly. Okay, so what is not being mapped from the domain to the codomain? That's the easy answer, right? All of them. None of the element of x is mapped at all. Okay, so that's a pretty clear, reason why it is not a function. So I'm just going to explain down here and say that, none of the elements of x is mapped, and as a result, this f is not a function. Okay, are we good so far? So the empty set in this case is not a function because we are supposed to map A to something, we're supposed to map B to something, and we're also supposed to map C to something, and yet it's not doing that. Okay, so it is not a function in this case. All right, let's take a look at another example. So this time I have, A1, B1, and C1. All right, there we go. All right, so this time I have f being a set of 3 elements. Each element is a 2-tuple, and they are certainly mapping something, right? So now let me just repeat the sentence, of what makes a function. Okay? A function is a set of 2 tuples, and it has to be mapping every element in the domain, in this case x, to one and only one element in y, in the codomain, which is y in this case. So now the question is, if I define x like this, is it a function? So I'll let you guys kind of think about this a little bit, okay? All right, so we got some yes and we got some no here, and I really like classes like this because the correct answer is not up for votes. The correct answer is the correct answer, but it's not based on voting. It's not based on popularity. Okay, in other words, this is a logic dictatorship. Okay, the answer is whatever is logically correct. The answer is yes, this f really is a function. Okay, so let's find out why it is a function. Okay, I think I know why you guys are saying no, but I will go ahead and explain. Okay, so the real question is every element in x mapped to one and only one element in y? Okay, that is the question. Well, let's double check. Okay, so we're going to do it one at a time. Well, okay, so let me explain. So let's do this one at a time. So now I'm asking, is element A mapped to one and only one element in y? Well, in other words, I'm asking, is 1 an element of y? Yes, it is. So mapping A to 1 is not a problem. Now we look at B, the second item in the set F. Okay, we look at B. Is B an element of the domain? Yes. And then we look at what is mapped to. Is 1 an element of the codomain? The answer is yes. Now, if somebody is saying, but 1 has been used already, then I will say, yeah, but 1 and only 1 does not imply uniqueness, okay? It is basically just saying it has to be exactly 1 element in Y. It doesn't say anything about whether that element can be used already. Can 2 things from the domain map to the same thing in the codomain? Absolutely. Okay, it doesn't conflict with 1 and only 1, because 1 and only 1 does not say anything about uniqueness. Onto is not 1-to-1. Well, I have to look up the exact term of what onto means in this context. So let's look it up. So onto in math. All right, so onto has to do with surjectiveness. So it is not, we are not quite defining surjectiveness in this case. So onto is not 1 and only 1. Okay, let me just write something else here, okay? 1 and only 1 really just means exactly 1. That's all it's saying. It doesn't say anything about uniqueness. All it's saying is exactly 1. Because if I don't say exactly 1, or if I don't say 1 and only 1, if I just say 1, then it is ambiguous, right? Because, okay, let's just say that I ask you guys, okay, how many people have 1 cat as a pet, okay? So now the question is, am I asking whether you have exactly 1 cat or at least 1 cat, right? So, but if I say that how many people have exactly 1 or 1 and only 1 cat, then I would not meet that requirement because I have 2 cats. All right, so Omar is saying there has to be at least 1 value in Y for each value in X. That is not correct. You can leave items in Y that are not mapped. It does not make that does not break the definition of a function. And then John is saying on the, so in other words, it can't be something like A12 and still be a function. That is correct, because A12 is a 3-tuple. You cannot have a 3-tuple. They have to be 2 tuples, because you can pick 1 item from the domain, you can pick another item from the codomain to make the 2-tuple. So 3 tuples should not exist at all. And then Omar is saying, but each value in X needs a corresponding value in Y. That is correct. But the way I define F in this case does meet that requirement. They just all correspond to 1 particular value in Y. That is correct. Also, Omar, you do not need to use all values in Y. That is correct. All right, and then Joshua is saying, so with the birthday example, multiple people can have the same birthday. 1 person can only have 1 birth date. So in that case, I think you're looking at people as the domain, and you're looking at each day in a year as the codomain. And it does make it a function, because every person has 1 and only 1 birth date. So if you look at how people map to dates in the year as their birth dates, that mapping is a function. Exactly, so Yalas is correct also, okay? This is equivalent to what we know as the vertical test in continuous math. But that's only for continuous, right? Because, if a function is not continuous, then the vertical test can be a little bit tricky. All right. Yeah, onto is a little bit different. We'll get to onto a little bit later, or surjectiveness. We'll get to that a little bit later. I think in linear algebra, it depends on the context. I'm guessing the context of onto is whether whether you can have vectors to span the same space or to span a particular space. But we are not dealing with that in this class, because linear algebra is actually continuous math, and we are dealing with not continuous math here. Okay, existence. Okay, so we'll get to surjectiveness, later. But right now we just want to know what makes a function a function. So I'll give you guys another example. So another example for you guys to kind of think about. So I'm just typing on the side here. This time we map A to 1, 2, B 1, and C1. There we go. All right, so now I'm asking the same question. If I define f to be a1, a2, b1, c1, is this f a function? Okay, so is f a function? So every time if I say f is a function, I have to say what is my domain and what is my codomain. All right. So we got one answer of no, we got no, we got no. Okay, so if this were up to votes, then the answer is no. But if it's up to logic, the answer is also no. And why is it no? Okay, so this is what we want to focus on, is can we explain using the terms that I have used in the definition of a function to explain why this particular example of an f is not a function. X is mapped to more than one y. Okay, so I think I know what Gary is trying to say, but the notation is a little bit questionable. Okay, so yes, so there exists one element in X such that it is mapped to multiple items in Y. Okay, in other words, it is not one and only one anymore. It is more than one. Okay, so I will put it in writing here. Okay, so give me a second here. Okay, so I'm gonna use the example here. So A in the domain X is mapped to more than one values in Y. Hence, f is not a function. Okay, so this is how I would explain it. Okay, so A, which is an element of the domain, if f was a function, then A should map to one and only one value in Y. But in this case, it is not the case, because we can see that A is mapped to 1, it is also mapped to 2. So there are two values that A is mapping to. 2 is not one and only one, and as a result, one of the requirements of being a function is not met. Yep, exactly. So if I were to use the same notation, okay, so I'm going back to an earlier example here. So I'm going to use the same notation here, and I will say A in X is mapped to nothing in Y. Hence, f is not a function. So in this case, where we need to be exactly 1, it was a 0 in this case. And in here, where it was supposed to be 1, we got 2, okay, or more than 1. So that's why neither the first nor the third examples make a function, but the second one does meet all the requirements of being a function. So are we okay so far? Is everybody understanding why when f is an empty set, f cannot be a function when x and y are both non-empty. Y, in the second example, f is a function even though all elements of the domain are mapped to the same value in the codomain. And also y in the third case, f is also not a function because one particular value of the domain is mapped to more than one item in the codomain. So is that okay so far? Is that all clear? Cool. Okay. But this is wordy. And wordy is not something that mathematicians like. Okay. So when you look at math, okay, I'm not sure how people look at math. Math is, for the most part, a language. Okay, it can do other things too. It is but it is, for the most part, a language by which we can reason out things. Okay, so that's kind of what math is. In other words, if I need to be wordy like this, okay, which can contain phrases that are ambiguous, because well, remember, at the beginning we got quite a few people misunderstanding what one and only one means. Okay, but that's only natural. Okay, because we don't use phrases in English in a very, very precise way. Okay, so that means this is not, okay, when I say this, I'm referring to the sentence. Okay, this is not the best way to describe what makes a function a function. Okay, we want to use a very precise and yet concise language to say what a function really is. So the rest of this module, hopefully you guys got some time to read through this earlier, okay, really is the derivation of the final result of what is a qualification of a function. Okay, so I'm going to skip all the intermediate steps, which are just kind of reasoning of how I arrived to the final form. So I'm going to skip all the way to the final form, which is here. Okay, so if a set F is meeting the claims to map, oh, okay, I see how this one is still not meeting all the requirements. Okay, I got to be a little bit more clear here. Okay, I just spotted it, so I'm gonna have to fix it right now. And this one is in the previous module. The reason why I have to fix this is Q is not, we're not binding Q to something in Y. So that's why we have to, I have to add something to it. So I'm gonna look for this part. So I'm making some adjustments in the text. No, I don't have to do that. Let me just kind of quit the editing. Okay, so I'm gonna explain why I don't need to change it. I thought I had to, but I don't have to. The reason why I don't have to is because we are making the assumption F is a subset of X, the Cartesian product between X and Y. So that already guarantees that for each element in F, okay, the first item in the 2 tuple has to come from X, and the second item from the 2 tuple has to come from Y. So we already meet that constraint by making the assumption that F is a subset of the Cartesian product of X and Y. But I do have to make one little change. Okay, so let me change that part. Okay, so I'm done with that change, and I'll have you guys to help explain why that change is important. Okay, so focus on this part, okay? And if I refresh, you see how the proper subset of is now changed to just subset of. Why do you think that is important? Or under what condition is this actually significant? Why do you think it is important for me to use subset of instead of previously a proper subset of? It only happens very rarely, okay? It's very rarely that it makes a difference, but it does make one difference, you know, when x and y, or when x is a particular size, or x has a particular cardinality. Okay, so let me give you an example. Okay, so we'll put my whiteboard back here. And I'll give you one kind of weird example. But it does, you know, it is one thing that we have to consider. Okay, so we are going to look at this and define, okay, we'll define x to be a set with only one item in it, just a in it. And we'll define y to be, yeah, I mean, y doesn't have to be limited just one. We can have 1, 2, or 3, doesn't matter. Like so. And now we want to define, okay, a function f so that f is mapping x to y. There we go. All right. So first thing is, how many elements do you think this f has? Remember, exactly one. Okay, very good, Alex. Okay, it has exactly one element. Okay. Now let me go back and change my y, the definition of y. So what if I change my y so that it only has one element too? What do you think is the size of f? What is the cardinality of f? Well, can I make a function? Okay, that's the first question. Can I make a function f so that the domain is the set of A and then the codomain is the set of 1? Can it happen? Okay, yes, okay, very good. Do I have any choices? Can I say, yeah, there are many choices. I can make f like this, and I can make f like this, and I can make f like this. I don't have choices, do I? Okay, in other words, the only way to make a function in this case is, you guys cannot see it yet because I'm still typing. So, but A has to map to 1. Okay, there's no other way to define the function. Yep, so Gary is right. Okay, f as a set containing the 2 tuple A1 is the only way. Okay, but in this case, what is the Cartesian product? Okay, what is the Cartesian product between x and y? The same thing. Okay, very good. Okay, so we want to make it clear, so that we want to say x times y is also just having a set having A1 as a 2 tuple. There we go. This is why I have to change the proper subset of symbol to a subset of symbol. Okay, this is why f is a subset equal of x Cartesian product with y, and not f is a proper subset of x Cartesian product with y. Is that okay? Does everybody understand why I changed the notation? because the original notation, which is a proper subset of, works in most cases, but not all cases. Because in the very rare cases where the domain only has one single element, then the proper subset of notation would not be true. So is that okay? Does everybody understand why I changed the notation? I'm hoping so. Okay, cool. All right. So with that done, okay, so now we want to look at this notation here. Now this notation is already making an assumption that f is a subset of x and y, the Cartesian product of x and y. So we already know that f is a subset of that Cartesian product. So what is left for us to do is to say, well, for everything in the domain, it has to map to one and only one thing in the codomain. So we'll take a look at this notation and try to figure out what it is saying. The first part, or the leftmost part, is saying, look at everything in X, okay? It has to satisfy whatever requirement is inside the parentheses. If you can find one element in X that does not meet this requirement, then the entire thing is false, okay? So the for all thing basically is saying, every single element of X has to meet this requirement. So now that we know that E, lowercase e is representing in a particular element of the domain, now we want to see what constraint we are talking about here. Now this looks kind of long and funky, but we just have to look at this we just have to peel the onion one layer at a time. So we are comparing the cardinality of something because we see the two vertical bars to 1. Okay, so we're trying to confirm that the cardinality of a particular set is exactly 1. Okay, so now we look at, okay, but what set are we talking about? So then we see this notation here, EQ bar EQ in F. Okay, so we are looking at a particular set, okay, that is constructed on the fly, where every two tuple that meets the requirement of the first item is coming from this X here, and then the second item is some Q, okay? But we also want to make sure that EQ as a two tuple is an element of F, okay? So every EQ that meets this requirement, okay, is in this particular set. And we want to make sure that the cardinality of that set is exactly 1. So what this is really saying is the same thing that we wanted to say, which is every element of the domain is mapped to one and only one. Okay, this is the one and only one here. Codomain item in the codomain, which is what Q is. So are we doing okay so far with this notation? How we define the qualification of whether f can be seen as a function or not. Okay. All right. So this is perfect timing. We got 3 minutes left, which is just enough time for us to think about, why the concept of a function is useful. Okay. So the example in this case is something that most people don't have to deal with, okay? But just kind of imagine that a professor is asking you to write a sorting algorithm, okay? So if I were just to say, okay, this is your homework assignment, I want you to write a sorting algorithm. This is the input array, array A is the input array, and I want you to do a in-place, sorting algorithm, so that when the algorithm is finished, array A would contain the elements in a sorted way, okay? And I just leave it like that, okay? And then most people would, well, okay, you guys already know what sorting is, okay? But someone may say, but I don't know what sorting is, okay? I don't know what qualifies as sorted, okay? So now I want to explain what is sorted in a mathematical way. So now one way to define whether an array is sorted is to use this notation here. Okay, so let's take a look at this notation. And A in this case is our array, which is kind of the same thing as a tuple that has many, many items. Okay, so let's take a look at this notation and see what it is really saying. So on the outside, we have the universal quantifier for all, and we use this variable I, and we are looking at a particular set here that is made out of natural numbers. It starts with a 0, and a dot dot is specifying a range. So it starts from 0, it ends with the cardinality of A, or the length of A as an array, minus 2. So every element in this particular set is a valid index of the array A, except for the index of the very last element. But we don't need the last element, because what I'm trying to make sure is A bracket I, element I of A, is less than or equal to element I plus 1 of A. And that's why we terminate one element short, because the last element of an array does not have a quote-unquote next element to compare to. So is that okay? Does everybody understand this notation? But if I use this to say, okay, this is the condition that if this condition is met, then the array is sorted. Okay, let's just say that I use this in a homework assignment. Well, if I did that, then I can write a very simple algorithm to meet this requirement. So let me use Mousepad, which is just a text editor, because I just want to type a program really fast. Okay, so now if I want to say F is an in-place sorting algorithm, okay, and we are just sorting integers. Okay, so let's say the array that we need to sort is just an integer array. So we have something like this, right? And we'll also specify the length of the array as a separate parameter, and we'll call that L, or len, as the length of the array A. So this is one thing I really do not like about C and C++, is when you pass an array to a subroutine, unless, okay, you say that, okay, the array has to terminate with a particular value, like a null terminator in the string, or you explicitly pass another parameter to specify the length, the array parameter itself does not say anything about the actual length of the array. Okay, this is one big thing about C and C++ that I really have a problem with. But getting back to what we want to do, okay? So now I can say, okay, I'll just use I as a local variable. For I equals to 0, I is less than length plus I. And then in this loop, all I have to do is to say A bracket I equals to 0. And I'll turn this in as my sorting algorithm. And then Mr. Professor Subsidiary will look at this and go like, no, this is not sorting. You're just reinitializing this array to all zeros. But then I'll say, but Iraj, this is meeting the requirement that you have laid out. Because the requirement that was laid out is this, right? So every element in the array has to be less than or equal to the next element in the same array. And by initializing the entire array to 0, guess what? It's going to meet this requirement. I'm done. Cool. Should I get points? For being able to argue, right? But for so why is this description not capturing an array being sorted? What is missing? Zero as a value may not be in the original array, right? Well, if Iraj is not taking this, but this is all he specifies as the requirement of a quote-unquote sorted array, he cannot argue because because I have just created an algorithm that meets exactly this requirement. So that means the requirement itself is the problem. I need something else. Okay, this is okay. It's a good starting point, but it doesn't capture the idea of sorting. Okay. All right, so yes, so Gary has gotten it in the text channel. All original data has to be contained in the output array, okay? So every value that was in the original array still has to be in the output array, okay? So now the question is, how do we specify that, okay? In other words, what Gary is saying in words, it's good, okay, but it still doesn't capture what we need to do. Okay, so we'll consider what Gary just said. Okay, we have to ensure all original data is present in the output. Okay, so that's what the homework assignment says. Okay, so if I switch back to my text editor here, okay, and this time I'm not writing an algorithm, but I'm just giving you an example. Okay, so if the input array is 0, 1, 0, 0, okay, this is the input array, and I'm supposed to sort the array in non-decreasing order, okay, which means it's supposed to be 0, 0, 0, 1, but if I use 0, 0, 1, 1, it still sort of meet the requirement of all the original data is in the output, because I got zeros and ones in the input and I have zeros and ones in the output. It's just a wrong count. Do we see how it's really difficult to use English sentences to specify the correct output, okay? So if you read the rest, okay, yep, okay, very good. So this is why we have math, okay? This is why we have mathematics, because it gives us the language, the vocabulary to express something like what we're trying to express here in a concise. Now, conciseness simply means that we're not being too wordy, which is good, but it's not essential. What we really want is precision, okay? Mathematics is a language with precision, okay? Now, we still don't have what it takes to explain, to somebody else what sorting really is, okay? But what we can get to this point is something that looks like this, okay? So K subscript something was the original value in A subscript something. So if I were to use this notation here, okay, so if we focus on this notation, this is how we define the K, the constants case, okay? They may not be unique, but the idea is Ki is the constant that has the original value of A bracket I. Okay, so now we have this notation to say what was in each position of the array when we got the array as input. Okay, so when we specify the output, we want this requirement to be met. Okay, for I being basically a valid index into the array, the output array, or the final form of the array in A bracket I, it has to equal to K, and then this is a function f applied to I. Okay, so we are using we're using the notation of a function to control how the output elements map to initial values of the input array. But it is still not concise. This is still not good. Okay, it's still not good because this function can map everything to the same element. In other words, all I need to do, if this is the requirement, that Iraj is specifying, and say that, haha, you have to meet this requirement on top of the other requirement. Okay, well, that's pretty easy, because if the characteristics of f is not stated, then I can just say, well, in that case, I'm going to assume this f is mapping everything to the same value. Then I go back to my algorithm, and all I need to do is to say that, and it would meet the requirement that is stated down here. Okay, because in this case, this particular function f is really just mapping everything to 0. And it will still be okay. So this is all trying to tell you, this is me trying to tell you, the next module that you need to read will help answer some of these questions. Because the next module that you're going to read, and I'm just trying to find out where we are, okay. Okay, so the next module is here, injection, surjection, and bijection, okay. This is where we look at functions and we classify functions, or we characterize functions into basically, it's really just two, because bijection means it's both injection and a surjection, okay, that's what bijections are. But we are now looking into extra requirements that we need our functions to satisfy, okay. And by the end of the discussion of injection, surjection, and bijection, then we will have the proper vocabulary to express what a sorting algorithm is supposed to accomplish. I don't even care how it is done, okay. You can have a big O and to the power of 4th super slow and inefficient algorithm. I just want to look at the output and be able to use a mathematical way to qualify whether your sorting algorithm is actually sorting or not, okay. So that's what we're going to do next Tuesday, is to look into injection, surjection, and bijection. So over this weekend, okay, now remember, you guys voted, okay, I know some of you did not vote that way, but we ended up having a 5-day weekend. So that means on day 3 of the 5-day weekend, it's probably a good time to review the content, the material, just to make sure that we are clear on concepts related to set operations and notations, what a function really is, the qualification of a function, and read a little bit ahead of time, okay, to understand what is injection, surjection, and bijection. I'm looking at the text channel, and Aaron is...
Yeah, but I'm not going to do that.
Right. So we voted on, on which days we're going to have the synchronous lectures, and the result was, Tuesdays and Thursdays, even though there are quite a few people, just not enough to vote for Monday, Wednesday, Friday. I was really kind of hoping for Monday, Wednesday, Friday, because I think having 3 shorter lectures spreading over more days in a week is a better way for people to absorb the information. But I'm guessing even more people want to have a longer weekend. Yep. Okay. But I have to respect the majority. I certainly hope the upcoming presidential election is going to be that way too. All right. So it still kind of works out, we just have to be mindful that the weekend is really long, and, spend a little bit of time of the weekend to review material that we have already talked about, especially the tricky stuff, the examples that I have shown, in on the quote-unquote whiteboard. Those are the really kind of fun ones, right? Because, that's, I'm trying to present things that looks like it will work or looks like it won't work, but it's kind of the other way around, okay? So that's kind of important. So we want to review the material, and we also want to read a little bit ahead of time, just so that we have a general idea of what are the topics that we'll talk about on next Tuesday. Yeah, vote by mail is at this point, I think I have more faith in vote by Google Forms. But we'll see. We'll see what happens in the election. Anyway, the live lecture part is done. Okay, so it is what 12:02 at this point. I'm gonna stop the live stream, but I'll keep an eye on the text channel. So you guys can keep using the text channel and chat a little bit and chat away, as long as nothing is being offensive. Okay, nobody is doing something nasty. You guys can keep using it. So I'm gonna stop the streaming now. There we go.